guys, nice to see everyone again, and we are now back to the topic of 7.1 but part 2 of it, where we will focus on drawing Lewis structure of a covalent compound. So we are going to be drawing a lot of Lewis structure of a lot of different covalent compounds. So it would be very, very great if you pick up a pen and some papers and start drawing together with me. Alright? Lewis structure is actually electron dot symbol that shows the bonding between the atoms of a molecule. So that is the Lewis structure that we are going to draw. And we know that in the previous video, your Lewis structure will have a very close relation with your valence electron. So the electron dot symbol that we are going to draw will also depends on the valence electron that we have. And for this video, I want to remind you again, we will be only drawing for covalent compound. And how can we draw a Lewis structure of a covalent compound? We have 6 steps, alright? I will give you all the steps and all the remarks that you need to take care of. So here is the 6 steps that you need to look at to draw a Lewis structure of a covalent compound. And the step 1 is this, step 2, step 3, step 4, 5, and 6. We will go through all the steps in the example straight away. But just a very kind reminder, make sure you read through the remarks, make sure you understand all the remarks, because all the remarks is very important rules and regulation to ensure the Lewis structure that you draw is correct. So let's start with the first structure. The first structure that we have on the screen is CH4, okay? And what is our step 1? The step 1 is going to total up the number of valence electron. So we are going to total up the valence electron for carbon and hydrogen. So let's count the total valence electron of carbon and hydrogen. Carbon over here is 4. Hydrogen valence electron is 1. But I have 4 hydrogen. So times 4. 1 times 4, 4. Therefore, the total valence electron that we have is 8 electron. It's very important to calculate the total valence electron correctly because it shows the total number of electrons that involved in the bonding. In the other words, it shows that the total number of electrons that you can put into your Lewis structure. Second, we are going to draw the skeletal structure and draw single bond. We need to determine who is the central atom. Central atom is the least electronegative or simple. If you look at CH4, obviously, carbon will be the central atom, bonded with hydrogen in the form of single bond. So we draw the single bond first. H, 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 and H. And in the previous video of the part 1, we know that one single bond, alright, consists of how many electrons? 2 electrons. So I have 4 single bond over here. Every single one of them is 2 electrons. 2 electron, 2 electron, 2 electron, and 2 electron. So I already used up 8 electron. You need to minus all the electron that you put in. So you minus 8 electron over here and you left 0. You have nothing left. In the other words, all the electron that you have, you already used in the structure. That is what we mean by subtract the number of electron involved in the bonding. 2 electron for a single bond. So you minus them already and there is no remaining electron. When there is no remaining electron, we are pretty much done. I say pretty much. We are not really done. How to ensure that we are correct or we are done is to check whether they are achieving octet or duplet. Why I mentioned the word duplet? Because I have hydrogen over here. Hydrogen is the only one that will achieve duplet. So, duplet means 2 electrons around hydrogen. And hydrogen right now, every hydrogen holding 2 electrons. Remember, one single bond is 2 electrons. So, hydrogen holding 2 electrons, hydrogen holding 2 electrons, hydrogen holding 2 electrons, and 2 electrons for this hydrogen. So, all hydrogen achieve duplet. In the other words, all hydrogen is stable. And if you look at the carbon, carbon need to achieve octet over here. Octet means 8 electrons around carbon. And if you look at the carbon, surrounded by 4 single bonds, and every single bond is 2 electrons. 2, 2, 2, 2. Total 8 electrons around the carbon. Therefore, carbon achieve octet. And since everyone in there is happy with duplet and octet, therefore, That is the Lewis structure of CH4. Simple. Alright, don't worry if you don't get it now. We are going to do a lot of exercise today with a lot of covalent compounds, so you will get it at the end of this video. Stay with me until the end. The second example that we have on the screen is H2O. So we are having H2O here. The first step is still to total up the number of valence electron. So the total valence electron for your H2O will be hydrogen equals to 1 times 2. Why times 2? 1 is because every hydrogen holding 1 valence electron times 2 over here. So you have 2. Oxygen. How many valence electron for oxygen? Oxygen is a group 16, so 6 valence electron. And therefore, the total valence electron for water is 8. In the other words, we have 8 electrons to put into your Lewis structure. And if you look at it again, H2O, who going to be the central atom? The central atom will be your oxygen holding hydrogen. Remember, we will start off with drawing a single bond for the skeletal structure. So draw the single bond and determine who is your central atom. In this case, between oxygen and hydrogen, even though oxygen is more electronegative, but oxygen will still be the central atom. And we already used 2 single bonds. So 2 single bonds represent how many electrons? 2 single bonds represent 4 electrons. Therefore, we already used 4 electrons. We need to minus 4 electrons. And 8 minus 4, we left 4 electrons. And the 4 electrons that you left over here, what can we do? Use the remaining electron in pairs to fill the octet of the terminal atom. What is terminal atom and what is central atom? Simple. Terminal atom means next to it there is nothing else, alright? Next to it there is nothing else. That is what we call terminal atom. So we have 2 terminal atoms over here. Both hydrogen is your terminal atom. Terminal, last stop. Okay, that is your terminal atom. And your oxygen over here obviously is your central atom. Your central atom means next to it, in between it, there is still bonding. So that is your central atom, that is your terminal atom. Use the remaining electron in pairs to fill the octet of the terminal atom. But if you look at our terminal atom over here, our terminal atom is hydrogen, and we know that hydrogen only achieves duplet. And we already have 2 electrons. Means this hydrogen is already achieving duplet. Alright, so we are done with the hydrogen. If we are done with the hydrogen, if there are still extra valence electron, I still have 4 valence electron, then put them around the central atom. And you are going to arrange in pair first. For this case, we are going to put them in the form of pair first. So I have 4 electrons, I will be putting them in the form of pair. First pair, second pair. Alright? And right now, if you look at your oxygen over here will then achieve octet after you put the 4 electron. And after you put the 4 electron, you will have no electron left over here. When you have no electron left, we check whether we achieve octet or not. So your oxygen achieve octet by having 2 electrons in the bonding. So you have 4 electrons in the bonding. And then you have 2 lone pairs. So total of it is your 8 electrons. That's why your oxygen achieve octet. In the other words, that is your correct Lewis structure for water. And if I want to draw it nicely, the correct will be something like this. So you have your lone pair. Okay? And that is the correct Lewis structure for your water. At the end of the day, make sure everybody achieve duplet or octet. The only one that will achieve duplet is your hydrogen. Make sure your hydrogen achieve duplet and the rest of the atom in there achieve octet. Let's look into another example. The third example that we have is CCl4. CCl4. Let's try to work out the total valence electron. The total valence electron for CCl4. Carbon is 4. Chlorine is 7. One chlorine having 7 valence electron times 4. So times 4. 4 times 7, 28 plus 4. Over here, you have 32 electrons that you need to put into your Lewis structure because that is the total valence electron that were involved in the bonding. I start off with my carbon. So my carbon over here will be the central atom. Okay, central atom must be the least electronegative atom. So C and Cl, carbon is less electronegative. Carbon, single bond with the terminal atom. My terminal atom is Cl, single bond, single bond, single bond, single bond. And everybody knows that one single bond is 2 electrons. So I have 4 single bond. When 4 single bond times 2 electron, I have 8 electron used already. So minus 8 electron over here. You already used 8 electron. You left 24 electron. Next, what do we do? After you minus the number of electron involved, you are going to use the remaining electron in pairs to fill the octet of the terminal atom. Before we check the central atom, we need to make sure that all the terminal atom over here, or your chlorine over here, must achieve octet. So your chlorine as a terminal atom over here, already having 2 electrons in the bond. You're already holding 2 electrons in the bond. So octet means 8 electrons. I already hold 2. So I need another 6 electrons. And we will start them by pairing up the electron straight away. So pair the electron, 2, 4, 6. And you can see right now your chlorine is now octet. 2 electrons in the bond and 3 lone pair around the chlorine terminal atom. So total of this chlorine is 8 electrons. The same thing applies to all the chlorine. You put in another 3 lone pair because every lone pair is 2 electrons. So 2, 4, 6 in the bond 2, 8 electron octet. Same thing. We are going to do the same thing to all the chlorine because your terminal atom now is the same. And since every chlorine is getting 6 electrons and I have 4 chlorine over here, so 6 times 4 is 24. And you need to minus 24 out from your total valence electron. 24 minus 24 and 0. Always remember, at the end of your Lewis structure, your total valence electron must go back to 0. That shows you already used up all the electron that you need to use up. Okay? So, we are proceed to the next step. We are done with this step. If they are extra valence electron, put them around the central atom. Do I have extra? No, I don't have any extra over here. So, we give a pass to this step. We are going to check whether it's octet or not. And if you look at it, all your chlorine over here right now is octet. So, your carbon, if you look at your carbon in the center having 2 electron in this bond, 2 electron in this bond, 2 electron in this bond, and 2 electron in this bond. 2, 4, 6, 8, octet. So, everybody is octet over here, and that is how your Lewis structure of CCl4 look like. Simple. Let's try another one. Okay. The next one that I have over here is PCl3. Again, guys, we will start off by total valence electron. Phosphorus, 5 valence electron, group 15. Chlorine, 7 valence electron, times 3. Okay. So, phosphorus is 5. Chlorine is 7 times 3, which is 21. So the total valence electron for PCl3 is 26 electron. And then, who is the central atom? The central atom must be the least electronegative. So the least electronegative is phosphorus. Alright, phosphorus in the center. We are going to draw the skeletal structure and single bond. So single bond to the chlorine, single bond to the chlorine, single bond to the chlorine. And we know every single bond is holding 2 electrons. 2, 4, 6. So we minus 6 electrons. And we left 20 electrons. And the next step, use the remaining electron in pairs to fill the octet of the terminal atom. So the terminal atom again is chlorine, the same concept like the previous example. You already have 2 electrons over here. So chlorine need another 6. So we put them in the form of pair, 1 lone pair, 2 lone pair, 3 lone pair. So 3 lone pair is 6 electron, 6 plus 2, octet. So the same thing apply to all the chlorine over here. Every chlorine again getting 3 lone pair to achieve octet. Every chlorine getting 3 lone pair to achieve octet. And since every chlorine taking 3 lone pair, and that total up to 18 electron. So we need to minus the 18 and we left 2 electron. Moving to the next step. If they are extra electron, then you need to put them around the central atom and you must arrange them in the pair first. Again, we will always arrange them in the form of lone pair. So 2 electron over here means how many pair? 1 pair. 1 pair. Remember, 1 pair means 2. So we arrange them in the form of pair. That is the 2 electron, the last 2 electron. So minus 2 electron and you are done, 0. So remember I said total valence electron must go back to 0. So we are done putting it in the central atom. Next, we need to check whether it's octet or not. And we can see over here all your chlorine is octet. 2, 4, 6, 8. 2, 4, 6, 8. And same thing over the chlorine top there is also octet. And your phosphorus is your phosphorus octet. And you can see over here your phosphorus holding 1 lone pair, 2 electron, and 3 single bond. So 2 electron, 2 electron, 2 electron. So you have 6 electron with 1 lone pair. So total 8 electron and phosphorus become octet. Therefore, that will be your correct Lewis structure of your PCl3. Make sense? Simple? Getting better? And you realize that for all this example, I only stop until step 5. We never really go into step 6. So the next example is talking about step 6. What is meant by step 6? And the next example we have carbon dioxide. Very simple structure, carbon dioxide. Always start off with the total valence electron. So total valence electron over here, carbon, 4 valence electron. Oxygen, 6 valence electron times 2. So you have 12. And the total valence electron over here, 16. If you cannot work it out spontaneous, we do what? We press the calculator. Don't do mistake on the total valence electron because everything that you draw is based on the total valence electron. So don't do it wrongly. And after you get your total valence electron for carbon dioxide, again, we start off with drawing the skeletal structure and single bond. So my central atom over here is carbon. Single bond with oxygen, guys. Single bond with oxygen. So when you single bond with oxygen, we are drawing 2 single bond. So every single bond represents 2 electron. So we minus 4 electron. And I left with 12 electron. So 12 electron, next step, after we minus the electron out, what do we do? Use the remaining electron to octet the terminal atom. So your terminal atom right now is oxygen. It's not octet yet because only holding a single bond with 2 electrons. How many more electron oxygen need? 6, because we need a total of 8 electron to achieve octet. I already have 2. I put in another 6 electron in the form of lone pair. 2, 4, 6 for this oxygen. Another 2, 4, 6 for the second oxygen. Put in 6 electron on the left and 6 electron on the right. That used up my 12 electron in total. Again, total valence electron 0. Okay? Next, if there is any extra electron, then you are going to put them around the central atom. But do you have any extra electron? No, we are done with that. Okay? Next, we are going to check the octet. Over here, you can see that your oxygen is already octet. Both of the oxygen, if you realize. 2, 4, 6, 8. Already octet for the oxygen. Same thing. 2, 4, 6, 8. Already octet for the oxygen. But it's your carbon octet. You realize that your carbon only holding 2 electrons from the single bond, 2 electrons from the single bond. In the other words, your carbon is only holding 4 electrons. Is 4 electron octet? No, it's not octet. But problem arises. I don't have electron anymore. My electron is finished. It's back to 0 over here. So where can I get electron to make it octet? Your step 6. If there are not sufficient electron available to complete the octet of the central atom, what do? We are going to move the lone pair of the terminal atom to form double or triple bond with the central atom. So we are going to form double or triple bond with the central atom. And what is meant by this is, we are going to move this lone pair from the oxygen to form a bond with a carbon. So I mean by this. You form a double bond with the oxygen, and the oxygen will lose a lone pair, but the oxygen will still remain octet. You can see over here why I say the oxygen is still remain octet. 2, 4, 6, 8. Bear that in mind, every single bond is 2 electrons. So you have a double bond, you have 4 electrons over here, and 2 lone pair. So oxygen is still octet. Okay? So there's nothing wrong to share the electron with carbon. And if this remain, is my carbon octet. You realize that your carbon right now is still not octet. Your carbon is only having extra 2 electrons. You have 2, you have 2, you have 2. So carbon right now holding 6 electrons is still not octet. How can I make the carbon octet? Is by moving another electron, another lone pair, to form a double bond from another oxygen. So your final Lewis structure should look something like this. Double bond with the oxygen on the left hand side, and the double bond will cause the oxygen to only have 2 lone pair left. And on the right hand side, you form a new double bond over here, and the oxygen as well as losing 1 lone pair, leaving 2 lone pair behind. And for this structure, your carbon right now is already octet because you have 2, 4, 6, 8. So your carbon right now having 8 electrons and your carbon achieve octet. Make sense? And the most important here, your oxygen remain octet. Both of the oxygen remain octet because you have 2, 4, 6, 8. 2, 4, 6, 8 remain octet. Simple. Alright, that is how your step 6 come in. Your step 6 means you already have no electron left, but your central atom is not octet. So how can we octet the central atom? Is by taking the lone pair from the terminal atom to go in, alright, and forming a double or even a triple bond later on. Okay, let's look into another example about cation and anion. So we start off with the cation. We have a cation of NH4 plus over here. What is meant by NH4 plus? It will change the total valence electron. If you read the remark, it will change the total valence electron. Positive charge form because you remove electron. So when you calculate the total valence electron, the positive charge need to minus the electron. For the cation, you need to minus the electron based on the charge. So what do I mean by this? Let's see how I calculate my total valence electron. Your total valence electron for this case will be nitrogen 5, hydrogen 1 times 4. So you have 4, and the total valence electron for NH4 is 9. But I have a positive over here. When you have a positive, the charge is positive 1. So positive 1 means we need to minus 1 electron. Because to become a positive 1, we remove 1 electron. So remove that electron, you left 8 electrons that you can play around with. That is how your cation or anion affecting your step 1. Bear that in mind, positive means remove electron. So you need to remove the number of electrons in the cation. Second is the same thing. We are going to draw the skeletal structure by using a single bond. And your central atom obviously is a nitrogen. So I start off with my nitrogen central atom holding 4 hydrogen. Bear that in mind, hydrogen. And the most important part is the positive charge. How to draw the positive charge in your Lewis structure? Simple. Bracket, square bracket, and then a positive charge. That's how we draw the positive charge in your Lewis structure. Okay? For a cation Lewis structure or for an anion Lewis structure, remember to put the bracket and the charge. Okay? Then only we proceed. So, you have 4 single bond over here. Single bond, single bond, single bond, single bond. 1 single bond, 2 electron. So, 4 times 2 minus 8. And you have 0. We are done with the electron. When you're done with the electron, let's check whether they achieve octet or duplet or not. Hydrogen over here achieve duplet. All hydrogen over here achieve duplet. You can see every hydrogen holding 2 electron in the bond, 2 electron in the bond, and 2 electron in the bond. Every single bond is a 2 electron. And nitrogen achieve octet. Obviously, because you have 4 single bond around it, and every single bond holding 2 electron. 4 times 2, 8. So hydrogen duplet, oxygen octet, and that is the correct structure of my ammonium ion, NH4+. The important thing that makes it different from others is the total valence electron. When it's a positive charge, you need to minus the number of positive charge because you remove that amount of electron to become that positive charge. Make sense? What happens if it's a negative charge? Next, we have a anion. And the anion we have today, silicon fluoride, SiF6 2-. 2-. Why we form a 2-? Because we accept 2 electron. So when you accept 2 electron, you need to add 2 electron in your total valence electron. So let's count our total valence electron. My total valence electron in this case, silicon is a group 14, so we have 4. Fluorine is a group 17, so you have 7 valence electron times 6. 7 times 6, 42 plus 4. You have 46 electron. But you are having a charge, guys. The charge is a 2-. Become negative because we accept electron. So the charge 2- will cause you plus 2 electron because you accepted 2 electron to become 2-. Therefore, total electron that you have, 48. And then we proceed, guys. We proceed with what? We proceed with very simple thing. The central atom and the terminal atom in single bond skeletal structure. My central atom, silicon. Skeletal structure with fluorine. 6 fluorine. Alright, so 6 single bond. And we all know that 1 single bond is how many electron? Okay, so 6 single bond over here. 6 times 2 minus 12. And after you minus 12, you left 36 electron. Okay, but before I proceed, bear that in mind, it's a charge. So when it's a charge, how your Lewis structure should look like. Your Lewis structure deserves to have a bracket, and also the charge 2-. That's how your Lewis structure look like. Okay. Then we proceed with, make sure the terminal atom is octet. So how can I make sure the terminal atom is octet? My terminal atom right now, the fluorine, holding only 2 electron. So holding 2 electron, I need another 6. And the 6 were in the form of pair, which means we are going to put in 3 lone pair for every single fluorine. So every single fluorine will have another 6 electron to achieve octet. I hope by now you should know what is actually octet and why are we doing all this. Don't skip the step and make sure you follow the step, and Lewis structure is easy. And after you octet all your fluorine, you put in electron into all the fluorine. Every fluorine taking 6 electron. I have 6 fluorine. So 6 times 6, 36 minus 36 electron. 0. Done. Finish with the electron. Check the octet. Fluorine. Obviously, everybody is octet. Why? We just make it octet. Alright, if you remember, 2, 4, 6, 8. And every single one of them are the same. So every single fluorine is octet. But is your silicon octet? Alright? Your silicon right now, around it, your silicon having single bond, single bond, single bond, single bond, single bond, single bond. 6 single bond. 6 times 2 means 12 electron around the silicon. And we know that octet means octet should be only 8 electron. So why silicon having 12 electron? And I can tell you that this structure is still correct. This is the correct Lewis structure of silicon. Why silicon can be 12 electron around it? Because we are moving to the next thing of this video. We have the exceptional cases to octet rule. We have 3 exceptional cases to octet rule. Other than 8 electron to the octet rule, we can have odd number octet. And what is meant by odd number octet? Odd number, obviously, we are having odd number. Odd number around the central atom. And even though it's the odd number, we will try to take as close as to the octet number, which is 8. So the odd number will be 7. We will take it as close as to the 8. And not everybody can have the odd number octet. Normally, it will only happen when the central atom is nitrogen or chlorine. Normally. It doesn't mean that all the nitrogen and chlorine center atom will become odd number. No. But if the central atom is nitrogen or chlorine, it might be the odd number. But of course, if we want to achieve octet. But if we cannot achieve octet, then we will take odd number octet. That is the first exceptional case to octet rule. We have second exceptional case to octet rule, which is incomplete octet. Knowing that your octet is 8 electron, incomplete means not enough. Therefore, you will have less than 8 electron around the central atom. And normally, it will be 4 or 6. Why 4 or 6? Because if it's an odd number, then it will become the odd number octet already. So, your incomplete octet will normally be an even number and less than 8 electron. Okay? So, it must be an even number and less than 8 electron, and normally it will be either 4 or 6. And this incomplete octet might happen to the compound where the central atom is beryllium, boron, or aluminium. Bear that in mind. Not every time there will be incomplete octet, but they can be incomplete octet if the central atom is beryllium, boron, or aluminium. We have a lot more incomplete octet, but what I'm telling you is those that in your syllabus only. Okay? Next and last but not least, we have our expanded octet. Expanded octet means what? More than you expanded. So you have more than 8 electron around the central atom. When I say more than 8 electron around the central atom, it could be 10, it could be 12. And normally it will only be even number. Okay? So 10 or 12, like just now, your silicon having 12 electron. So your SiF6 in your previous example is actually your expanded octet because your silicon is holding 12 electron around it. Why silicon can be expanded octet? Simple, because silicon is located in period 3 and above. So who can be expanded octet? When the central atom is located in period 3 or above, like period 4, 5, and so on. Why? Because in the period 3, 4, 5, and above, you have the presence of your d orbital. When you have the presence of d orbital, for example, 3s, 3p, 3d. So 3s maximum 2 electron, 3p maximum 6 electron, 3d maximum 10 electron. So with the presence of 3d, you can hold maximum 18 electron, more than your octet. So you can achieve 18 electron. When it's more than your octet 8 electron, that's why we call it expanded octet. And why it only can happen to period 3 and above? Because your period 1 can only be 1s2, which is your duplex. And your period 2 can only be 2s2, 2p6, which is only your octet. Only those central atoms that have d orbital can achieve expanded octet due to the presence of the d orbital. And d orbital only exists when it's above period 3 or in period 3. Okay, simple. And we will go through example for each and every one of them, so don't worry. We'll look at the Lewis structure that can have odd number octet, incomplete octet, and expanded octet. So let's start with odd number octet. And we know that odd number octet means it must be 7 electrons around the central atom. And the first example that I have for today is ClO2. Bear that in mind, when the central atom is chlorine, alright, chlorine or nitrogen, it can be odd number. It might be odd number. So we will see. We don't have the steps already, but I hope you remember the step. We still start off with total valence electron of ClO2. Chlorine, 7. Oxygen, 6 valence electron times 2. You should be extremely good to determine your valence electron. And if you don't remember the valence electron, you can actually work out the SPDF notation. And then from that, you can work out the valence electron. So, the total valence electron of oxygen over here is 12. 6 times 2, 12. The total valence electron for the entire structure is 19. Okay, it's an odd number. So, the total valence electron also an odd number. Your central atom, Cl. Skeletal structure with the oxygen, single bond, single bond. Okay, so single bond holding 2 electron, 2 electron, 2 electron. I minus 4 electron. 19 minus 4, I have 15 electron left. The next step, if you remember the next step is to make sure your terminal atom, alright, bear that in mind, that is your terminal atom, achieve octet. So, oxygen already holding 2 electron, we need to make it octet by giving another 6 electron around oxygen in the form of lone pair. The same thing to this oxygen, we are going to give 3 lone pair to make sure all the terminal atoms are now octet. So 6 electron, total 12, minus 12 electron. You put in 12 already, you use up 12 already. So we left 3 electron. And if you remember the step, if you don't, make sure you open up your notes. After you octet everything and you still have remaining electron, where do we put in? We put into the central atom, but you must put them in the form of pair first. So you will put 2 electron first in a pair, 2 electron, but I still have 1 left. Then only the one you put in single. So you minus 3 over here and you are done, 0. And if you think you are done, you are not yet. Before we are done, we need to make sure we check the octet. Is oxygen in octet and is chlorine in octet? So let's check for oxygen. Oxygen holding 2 electron in the bond, 6 electron as a lone pair. Over here, same 2 electron in the oxygen, 6 electron as a lone pair. So total 8. Oxygen octet, done. Chlorine having 2 electron over here, 1 electron over here, 3, 4, 5, 2 electron in the bond, 2 electron in the bond. So total chlorine having is 7 electron. And if you look at 7 electron is an odd number. It could be odd number. And if you check, it's a chlorine center atom. So chlorine center atom can be odd number. Therefore, chlorine will be odd number octet. And is that stable? Yes, your structure is correct and they are stable. Because chlorine can become odd number octet. Okay, so your ClO2 structure will look something like this. That will be your final structure of your ClO2 and is absolutely balanced because chlorine having 7 electrons around it and therefore it achieves odd number octet. And that is odd number octet. Let's look into incomplete octet. Incomplete octet again means that it has less than 8 electrons around the central atom. It could be 4 or it could be 6, where the central atom most likely going to beryllium, boron or aluminium. Let's see the example that I have. The example that I have today, aluminium chloride. So let's see, is your aluminium chloride going to be incomplete octet or not? Again, we will start off with the total valence electron. So your total valence electron, aluminium is a group 13, so 3 valence electron. Chlorine is a 7 valence electron times 3 because you have 3 of them. So the total valence electron of chlorine is 21. 21 plus 3 of the aluminium. Total valence electron of this compound is 24. After you have the total valence electron, we are going to draw the skeletal structure and determine the central atom. So your central atom today is your aluminium. The terminal atom is your Cl, Cl, and Cl. Okay? And we are going to minus the bonding electron that you put in. The bonding electron is single bond, and we have 3 single bond. Every single bond is a 2 electron, if you remember. So we minus 6 electron. And we left with 18 electron. And the next step, what are we going to do? We are going to make sure all the terminal atom is now octet. So we make sure all your chlorine right now is octet. Your chlorine already holding 2 electrons in the bond. So what do? We need another 6. So we put in the 6 electron as always in the form of lone pair. Okay, you should be extremely good at this right now, knowing what to do after every step. Practice makes perfect, guys. So don't memorize, but keep doing. Okay, so you have 6 electrons each on the chlorine. 6 plus 6 plus 6. I use up 18 electron and I have left nothing. You don't have any extra electron to put into the aluminium. It's proven that the total valence electron that you have is only 24 and you already use it up in this structure. You don't have any extra. So you cannot put any more electron in the aluminium even though it's not octet yet. So you can see over here your chlorine is already octet because 3 lone pair with 2 electron each. So you have 6 electron as a lone pair. And then you have a bonding electron over here too. So all chlorine is octet. But you realize that your aluminium only having 6 electron around you. Aluminium with 2, 2, 2. Aluminium only having 6 electron. Not enough. We need 8. So what happened is incomplete octet. Because aluminium can be incomplete octet. Aluminium is qualified to be incomplete octet. Therefore, aluminium can be incomplete octet. Okay? And there is no wrong. But bear in mind, not everybody can be incomplete octet. The incomplete octet is restricted to beryllium, boron, and aluminium only in your syllabus. Okay? So remember, not everybody can become incomplete octet. Only a certain people can become incomplete octet. And in this example, our aluminium become incomplete octet because it only has 6 electrons around it. Therefore, it achieved incomplete octet, and this structure, this covalent compound is still stable. Okay? Simple. Make sure you know the step. Make sure you can calculate the total valence electron correctly. Don't do mistake in your total valence electron because all your structure, your entire structure, is depends on the total valence electron that you calculate. And last but not least, let's go into the last exception of octet rule, which is your expanded octet. And we know that expanded octet can happen to many people as long as they are in the period 3 or above. Period 3 and above means period 4, period 5, and so on. Okay? But in your syllabus, I think we'll focus more on period 3. More than 8 electrons around the central atom. That normally be 10 or 12. Okay? And let's see the example that I give to you. The example that we are going to discuss today. A very favorite question. SF6. And as always, we start off with the total valence electron correctly. Sulfur having 6 valence electron around it. Alright, it's a group 16. And then your fluorine having 7 valence electron around it. So fluorine will be 7 times 6 because of 6 fluorine exists over here. So work out your mathematics. Over here is 42 and plus with 6 total valence electron is 48. Make sure you calculate that very, very correctly. Next step, we are going to draw the skeletal structure. So S, F, F, we have 6 fluorine. So make sure you put in all 6 fluorine with only a single bond at this moment. Alright, that is your skeletal structure. We have used 6 single bond, and every single bond is 2 electron. So 6 times 2, 12. Minus 12 electron out, you have 36 left. And the next 36, we are not going to put into the central atom first, because terminal atom must be octet first. So we need to make sure that we octet the terminal atom. Your fluorine right now, every fluorine holding 2 electron in the bonding. As always, we need another 3 lone pair to make sure your fluorine is octet. So always remember, we must always octet the terminal atom before the central atom. So your terminal atom deserves to be octet first. And right now, your terminal atom O is octet with 8 electron because we put in 6 electron into each of the fluorine. So 6 times 6, I use up 36 electron. And therefore, my total valence electron is finished. And the electron that I have used it up. And then we can check whether your fluorine is octet or not. Or your fluorine having 8 valence electron around it right now. So, or your fluorine is octet. You can see because from the bonding, 2 electron. And then you have the lone pair, lone pair, lone pair, lone pair, lone pair, lone pair. So, fluorine is all octet. But if you look at sulfur, sulfur having 2 electron, 2 electron, 2 in the bond, 2 in the bond, and 2 in the bond. And I have 6 bond, guys. So, sulfur will be having 12 electron around it. And when sulfur having 12 electron around it, sulfur is located in period 3. Therefore, sulfur can become expanded octet because the presence of the d orbital in the period 3. The SPDF notation for sulfur is something like this. So you can see that your sulfur is in the period 3. Your N highest is 3. So when you are in the period 3, you can have the presence of d orbital. And when you have the presence of d orbital, sulfur is able to achieve expanded octet. Is that clear? So this entire video is about drawing Lewis structure. So don't forget about all the rules and regulations that we have to draw this Lewis structure. We don't really need to memorize all the steps, but you will eventually get it when you do more exercise. Just be very careful with all the remarks that I have for you over here. Read through the remarks. There is some specific cases for like cation and ion, and how do we work out the total valence electron and so on. Okay? And my last reminder for you is make sure your total valence electron over here must be correct before you proceed to draw your Lewis structure. And again, thank you for watching this video with me. I really hope that you understand how to draw a Lewis structure for a covalent compound at this point. And if you have any question, feel free to drop a question in the comment below. And if you understand this video and if this video helps you, do give me a like and remember to subscribe to my channel. And I'll see you in the next video. Thank you.